Okay, welcome back again. We've talked about the cytoskeleton, and what we're going to do here is take a look at some proteins that work with the cytoskeleton. And here we're working with the actin filaments or the microtubules. And these proteins help to move things around in cells or create other forms of motion. And that kind of motion or movement can lead to things like contraction. Now, these proteins are incredibly dynamic. They are moving. They're actually proteins which are motors. And so they're going to be moving a lot. Very difficult to describe with static images. So I've got a lot of movies on the motor proteins canvas page. I recommend that you get in there, take a look at those, and you'll get a better idea of the dynamics of these proteins. And then these are going to come up several times during the semester, so we'll be coming back to these as they come up in some context. So the main function here of motor proteins is, as you expect, movement. It's motion. So we're going to look at some examples to talk about motor proteins. Huge family, ginormous family of proteins with a lot of diversity, working in slightly different ways to do slightly different jobs. So we're going to look at a couple of examples to kind of exemplify some of the general trends you see. So let's start with this protein myosin. And myosin is probably one of the most famous motor proteins because it's involved in muscle contraction. And in muscle contraction, it works with the actin filaments. So when you take physiology and you start looking at muscle structure, you've got to come back and revisit this in a lot more detail than we're going to cover here. So here's a myosin protein, and it's got some discrete regions. This part of the protein is the tail. Now let's just go back to talking about protein structure. This is very stylized. It's a model, it's a diagrammatic representation of what the artist thinks the molecule looks like. So it's a model of what we think the machine actually looks like. So think about it, you've got a chain of amino acids and it folds up, and so we've got secondary structures and tertiary structures forming, and so these are all pieces of the protein with discrete regional structures, and those are often called domains. So we've got a tail domain, and the function of the tail is to bind to other molecules, not to the cytoskeleton, but to other molecules in the cell. So that could be a cargo, it could be a vesicle. We talk about vesicles in a little bit. It could be a vesicle. It could be a vesicle full of neurotransmitters being moved along a filament in the cell. So there's the tail. There's a hinge, and the hinge flexes just like your joints flex, and so the hinge can flex. And so if we think actually about, my arm here, here's the tail of the motor protein, and forget I've got a shoulder and everything. Here's the tail, here's the hinge, and then here is the head. And the head is what binds to the cytoskeleton, and here it's going to be actin. So the actin filament will be down here in a moment. The important thing about the head is it's what generates the movement, and so it's going to be doing this. And you can quite easily see how that little flipper motion can be translated into different types of movement. Now to do that, that's work, and so the head is going to bind ATP, and so when we break ATP down and we move that phosphate from ATP, which we'll talk about later, when we do that ATP breaking down, we release some energy, and that energy can be used to do this mechanical work. So let's look at what myosin does. And we're not going to look at muscle in detail here because that gets too complicated very quickly. Let's just look at one myosin with one actin, and then you've got to imagine that in muscle there are hundreds and hundreds and hundreds of these molecules working together. So here we've got our red actin filament. So we talked about actin filaments before, minus end over on the left, plus end over on the right, two strands of individual actin monomers. So each of these red balls is an actin protein folded up, stuck onto another actin protein. A lot of people think that these are amino acids. They're not. They're individual actin proteins. So the protein is going to be made by the ribosome. It folds up, and we have a discrete protein. So what happens here is that the head is going to bind to the actin. Okay, and so the head can either be bound or unbound. Okay, so let's just say that the head is starting off kind of cocked back like this, and it's bound to the actin filament, and it lets go of the actin filament, and then it when it lets go, it cocks forward, so it's in this position, and then it can bind again to the actin filament, and it can cock again. So either the motor protein can kind of crawl along the actin filament, or it can cause the actin filament to kind of be pushed under it. So there's two types of motion. So myosin here is moving towards this end. And so it's called a plus end directed motor. So that's how myosin works. Let's take a look at another type of motor protein. The type of motor protein here is called a kinesin. Now it has the same basic structure that you saw in the myosin, except we've got a little bit more complexity. So rather than having just one protein, now we've got two proteins associated with one another. So we can again talk about quaternary structure from our discussion about protein structure. So we've got two discrete molecules, two protein molecules associated here. And you can see that there's a head here, and then there's this kind of winding tail that's bound to this cargo molecule. And that cargo molecule could be anything, like a little sack of neurotransmitters that's got to go from one end of an axon to another in a nerve cell. And so here's our cargo. So the tail of the protein is bound to the cargo. Here's the tail, there's the hinge in there, and there's the head. But here's the big difference between myosin and this protein, which is called kinesin. There are two of these, and the tails are wound around one another. So the two heads are kind of sitting like this, and then the tails are wrapped around one another. And I can't do that with my arms, obviously, but you can see how the tails are wrapped around, and then the cargo is stuck on the end of the tails. Now, these are doing exactly the same thing. They've got this cocking motion. They go backwards and forwards. Now, when these get coordinated, they can do this kind of thing, and that's like walking. So this thing can basically walk kind of towards the camera. You can walk along the microtubule. So again, this is a plus-directed microtubule. So that's kind of the kinesin protein. Some beautiful examples of this in the animations in Canvas. We can also put multiple myosin proteins together, and this is what happens inside your muscle. You get these large groups of myosins working together, and now you can generate a lot of force. So if we bundle some actin together, and we're just showing one fiber here, and we have these heads all cocking simultaneously, you can imagine the force that's generated to pull that actin filament back. And now we've got the basis of muscle contraction, where we're pulling the actin filaments, and that's going to give us contraction. We can also generate other kinds of motion using these motor proteins. So if you get into looking at the flagella and the cilia, this is what you're going to see working inside the flagella and the cilia. So if you've taken a look at that, then this will kind of make a little more sense. And you've got to go back and look at flagella and cilia if it hasn't. So if you think back to the flagella has got these arrangements of microtubules. So it's kind of like long shaft, and inside there are these pairs of microtubules, and there's 9 pairs and then 2 in the middle. So the microtubules are connected by these bridging proteins called linking proteins, and then the microtubules are anchored to a structure inside the cell. Now these flagella kind of extend outside the cell, and they're going to do this waving structure. So how do we get this waving motion like this using a motor protein? Well, before we allowed the motor proteins to kind of walk, is what we're going to do now is we're going to anchor the microtubules. So the walking only works when the motor proteins are free, so that the motor protein is going to be free on one end to walk. What we've done now is we've anchored sets of microtubules, and we've anchored the heads to one microtubule and the tails to another microtubule. So instead of being a cargo, you've got the tail stuck on another microtubule. So now when these motor proteins try and walk, rather than being able to walk along something, is what they do is they create bending or flexion. So if you try and kind of if this is the microtubule, if this hand is the microtubule and this is the motor protein, if I try and force this microtubule to move up and down, and it can't because of all these bridging proteins and this attachment inside the cell, rather than moving up and down, you actually create bending. And so if we're doing this bending thing, now we've got this kind of motion, and that's what you get in a flagella. Lots of this along the length of a long sperm flagella, for example, gives you this behavior. That's what gives you swimming. So it doesn't matter how we consider the behavior of motor proteins, they're always involved in movement. Okay, so that's all I want to say about motor proteins. I'll catch up with you guys next time.